So we discussed how bad a life lock or divergence is for the new events to really happen indefinitely often, so that you don't really have a chance for the old events to really occur. That's basically what a divergence or life lock is. And really make sure you understand the intuitive introduction I made to you in the last part. And now we'll talk about exactly how we can prove formally that divergence is actually free from your model. Right? Let's see exactly how that can be proved. In order to do that, we need to define a new construct called a variance, right? As opposed to invariance. Think about the literal meanings over here. Invariance is simply something that will never change. On the other hand, variance is really something that should really keep changing until a certain level or certain value, right? That's something you want to keep in mind always. Right, so the proof obligation rule for non-divergence or life lock freedom, you can say either way. There are two parts that we would like to do, but I'm going to talk about the proof obligation themselves maybe in the next part of the lecture. But for this part, I would like to show you exactly how to manipulate the variance. So I also got some exercise later to really for you to think about, what if I give you a particular variance, how can you actually show whether or not that variance will actually work for your model. So that will definitely help you think about how you can come up with a variance for any arbitrary model. I'm pretty sure that will be the question you're going to have for me at some point. So that the exercise I gave to you will be my answer, just to try out different possibility for the variance, right? But for now, let's now talk about how we can use the so-called variance over here. As I said, from the literal meaning, variance simply means some expression or something that should really keep changing, as opposed to invariance. So we want to use the variant. So this is a very important definition over here. I'm going to demonstrate to you exactly what that means. It might sound a little bit abstract or vague over here. We know that the new events may simply interleave indefinitely, as we saw earlier. But we want to use a variant integer expression to really characterize exactly this kind of interleaving. And we want to make sure such interleaving should be finite, and it should be bounded. It should not be indefinite. Right? That's kind of the idea at the highest level. And a variance, formally we're gonna use V, capital V standing for variance. The variance may refer to either the constant C, or do you remember what W is? Is it an abstract variable or a concrete variable? Right? It should be concrete variable, right? So we only worry about the variance in the context of refinements. So that's why W here is actually the concrete variable, right? That's the formal components we covered earlier. I'm going to leave the review to you if you need to recall the detail. So the variance may refer to concrete variables. That's very important over here, right? And also, let's say we have this variance over here. And since your very first exercise about the variance, I'm going to give you right away. Let's take it for granted. But I think at this point, it's more important for you to really grasp the idea about why the variance expression can really characterize the interleaving of the new events interleaving. Why? That's something we want to see. All right, so just remember this variance expression over here is integer. You can see 2 times the value of A plus B is definitely integer for sure. Let's now switch to some illustration over here, right? This is our concrete model. And by the way, this model here is a different one than the earlier one we spoke about over here. Don't get confused. The earlier one was created just for the illustration for divergence. So forget about that model at this part, okay? For this part over here, we're going to use the original model, which is actually okay, right? And let's just remember we got 2 categories of events that we have to distinguish. This part over here are the new events, which do not exist in the initial model, right? It's really important because when we illustrate the variant expression, you will see how the variant value should really change depending on whether it's a new events or old events. So these are the new events, right? Whereas these two, let me just use, how about blue? So these two are the old events over here, right? These two, right? Just make it very clear to yourself about which events it is, which category it belongs to, right? So these two are the old events, which simply got overridden or redefined in the refinements, right? And the variant the variant expression that we spoke about earlier was 2 times A plus B, right? Since a bit arbitrary, but it's actually not, as we illustrated. So we want to say this global expression. Think about this global expression, which might change its value whenever any event occurs. Okay, so over here, so this is a global expression evaluated after each event's occurrence, including the new events and also the old events. Right? It's also very important for you to actually keep that point in mind, which I'm going to highlight. Global expression. That's especially important. Right? It's global and also after each event occurrence over here. Right? So let's now, I already got some trace over here for us to really evaluate. Let me just set up the context for us so we can trace very rather straightforwardly. This is a trace inits followed by ML out, two old events, and then we got ML in, we got IL in, IL out, IL in, IL out, and somehow that variant, it can be sure that once we get to this point, we can no longer actually got IL in or IL out, the new events enabled anymore. And then we must actually have some occurrences for the ML in, ML in before we can go any further with the new events. That's kind of the global picture we want to see. But let's now watch out exactly how the variance value is going to be evaluated after every occurrence. Let's now see that, right? You can see the V, it will be the value for the variance, which depends on, in this case, the value for A and B. But I simply put A, B, and C over here anyway, right? Just so we can do the complete tracing. This is a little bit different from the state transition diagram I did earlier, but I think that this will also work. Just easier for me to draw. Also easier for you to practice yourself on a piece of paper, right? You can definitely choose either way. Let's now try to trace it, right? So now, what's going to happen after the inits events? That one's easy. We simply got 0, 0, and 0. In that case, what will be the value for the variance? 2 times 0 plus 0. That will be simply just 0. And as we actually trace how the variable values and the variance values actually change, we can also use this graph to help us understand exactly how things are going. Let's plug in the numbers to the graph as well. So the vertical axis over here is the variant value, in this case 0. And the horizontal axis records the individual occurrences for each concrete events. So when I say concrete over here, I meant either old or new events, both, right? So let's see exactly how it's going to go. But for the first one, you can see for the inits over here, that actually got a variant value simply just 0. So inits over here. Okay, that's the first one. And there's something I want to mention as a side note over here. Think about exactly what this trace is really representing. Is definitely a valid scenario for our model, right? So after the initial system is launched, we're going to have our first car coming out of the mainland. The second car coming out of the mainland. And then this first car from the bridge actually goes into the island. And the very same first car actually goes out of the island. And then the second car on the bridge goes into the island. And the second car goes out of the island. And somehow now two cars are both on the bridge. And then the first car goes back to the mainland. And the second car goes back to the mainland. That's exactly the scenario, right? Even though I'm just saying that verbally, but I'm pretty sure you can imagine how exactly it is working. But you can definitely refer to the abstraction diagram that we did earlier just to make sure you understand this trace. It's quite important, all right? Let's now keep tracing. The next event is ML out over here. And that one there, by definition, is going to increment the value of A by 1. So from 0 to 1. And remains 0 for B and C. And what's the variance value? 2 times 1 plus 0, which will be 2. Right, so that'll be the value for the variance after the first occurrence of ML out. Right, let's do one more, and then we can plug both points at the same time. What about ML out again? In that case, it's going to be, for this one here, it's going to increment the value of A further from 1 to 2, and 0 and 0. Right? In that case, what will be the variant value? It will be 2 times 2, right? So that'll be 4 plus B, which is still 0. So that's 4. So we got this, right? So let's see exactly what's going on over here in the graph, right? So after the first ML out, I'm just going to put it over here. So ML out, and also ML out over here, right? So we got two occurrences. And the first one is going to increase the value of the variance from 0 to 2. From 0 to 2. So you can think about maybe around here is 2, 0 to 2. And then from 2 to 4. So that will be for the second one, right? So far, so good. And we're going to see, you can see for the old event, it is seen to be increasing the value for the variance, starting from 0 up to a certain positive number. And let's see exactly what the new events occurrences is going to do to the variance. We're going to see, right? And remember, the variance, the process of so the purpose for the variance is somehow to bound the maximum number of interleavings between the new events. We don't really want to say IL in, IL out to be indefinite. We want it to be bounded. Let's see exactly how the variance can really measure their progress. That's very important for you to observe. All right. So the next one is going to be, let me use the red, right? It's going to be ILN over here. ILN, by definition, is going to decrement the value for A and also increment the value for B, right? You can see that, right? So A decrement its value 2 to 1. And also B will be 0 to 1. C remains to be 0. And what will be the value for the variance? 2 times 1 and then plus 1, which will be 3. That will be value 3, which is strictly less than the earlier value, right? You can see after the first occurrence of ILN, okay, I'll say ILN, all right? In that case, the value will be decreased to 3, all right, over here. And what about the second one? What about IL out? IL out, by definition, is going to decrement the value for B, increment the value for C, right? A remain unchanged, B decremented to 0, C incremented to 1. What about the value for variance? It's going to be 2 times 1 plus 0, which will be 2. Right? In that case, it's strictly decreasing again. So after the next occurrence over here, right? Let me move this guy here a little bit down, right? After the second occurrence for the new event, which is IL out, I'm going to say IL out. The value further decreases to 2 over here, right? Hopefully you can now see the pattern over here. And can you just imagine what's going to happen after another 2 events over here, the new event, the same, right? So for ILN, if we do it once more, let's calculate them very quickly. For ILN, we're going to decrement A. From 1 to 0, increment B is going to be 0 to 1. And C remain the same. What's the variant value? 2 times 0 plus 1 will be 1. Strictly decreasing again. Right? You can see it's a very perfect trend that we're actually observing. So it's going to be another occurrence of ILN, which is going to be around over here, right? The value 1. And what about the last one, IL out? In that case, it's going to be decrementing B from 1 to 0, incrementing C, 0 to 1. A remain to be 0. What will be the variant value? 2 times 0 plus 0, which will be 0. So now we are really reaching basically the minimum value for the variance. We really want the variant value to be non-negative so that once we reach the 0, we are not able to really progress anymore by taking the new events. Okay, so there'll be IL out, right? It's going to be like exactly over here. So you can see so far the trend has been like this so far. You can see we start from this and we decrease all the way to 0 over here. And it's really important to say to see that over here, this part over here is really contributing by the old events, and this part over here is really contributing by the new events. Right? That's really important to observe. Right? Let's now let me write it down. So this is about is really contributing by the old events occurrences. And then we actually got this part over here would be the new events occurrences. And because we actually got proper guards for our new events, if you actually at this point, you can see this is the value for all the variables, right? You can see neither ILN nor ILOut will actually have their guard being enabled. A larger than 0, false. B larger than 0, false. Right? You can see both of their guards were simply falsified, so that means they are disabled at the moment. So we cannot take any further occurrences for the new event. So we are effectively preventing divergence. Right? So it's really important to highlight at this point over here. So let me put it here. Right? You can see after this point over here, no further occurrences are allowed for the events, for the new events. No further occurrences of new events allowed. Right? Effectively, we are preventing divergence. Okay, this is actually actually allowed. So we are really preventing divergence. Let me also try to write it down for you, even though I got very limited space, but I will try. How about over here? All right, so this part over here is really about preventing divergence. The main lesson for you to learn from this part of the lecture is really to see how the value for the variance over here can really measure the progress about what's the maximum number of interleavings you can take between any new events, right? Because every time you actually take a new event, either ILN or ILOut, in that case, it's going to strictly decrease the value for the variance. And we'll formulate this and generalize this in the next part, all right? So now here's a question. We know that at this point, we can no longer take any new events, occurrences. Does that mean the system deadlock? The answer is no, because we know that the variance is now decreased all the way to 0. So what we want to do is, before the new events can really occur again, there must be some old events occurring to really increase the value of the variance, so we can further take any new events. That's the idea, right? So that's why you see over here, we got 2 more occurrences for the old events over here, MLN and MLN, right? What about these 2? Let's take a look at them very quickly. But before that, I would like to fix 2 typos which I made earlier. Right? You can see after ILN, after ILOut, the C value over here is 1, which is correct because now we got 1 car on the bridge heading back to the mainland. However, after the second ILN over here, it's not supposed to decrement the value for C. Somehow I put it 0. So this is the first mistake I made, right? I'm going to fix that. So this part over here should be actually 1. You may have noticed that earlier, right? So this should be 1. And then what about the second occurrence of ILOut? In that case, ILOut is actually going to increment the C value from 1 to 2, right? So that's why this part over here should be 1 to 2. And this will definitely make sense because this means at the moment we got 2 cars on the bridge going back to the mainland. That's basically what's happening, right? So just make sure you understand exactly what I'm fixing over here, right? Let's now move on. About MLN and MLN, just about 2 cars going back to the mainland. In that case, you will just keep decrementing C by 1, whereas A and B will be untouched, right? So what we will do is we're simply just going to do A and B over here. So C will be decremented to 1 and then decremented to 0, right? In that case, does the variant value change? In this case, it does not, because you can see 2 times A plus B. 2 times A plus B just remain to be 0. C, in this case, is not relevant to the evaluation for variance. So in that case, we'll simply keep the value of 0 and 0. So that means after this, we got 0 over here and 0 over here for MLN and also MLN, right? They simply remain to be the same, which is okay, right? That's something we'll talk about later when we actually formulate the condition. For the old events over here, you can either maintain the value for the variance or you can actually increase the value for the variance so that you will actually make sure the variance value is actually above 0. In that case, the new event can start occurring, right? So the little exercise I want you to do is, at the moment, you can see after this point over here. So this will be the exercise I want you to assign to you. After this point over here, after the entire trace, we may just continue, right? So let me try to do write down the exercise over here, right? That's the best I can do over here, right? Actually, let me just try to go a little bit higher over here. Okay, so this will be the exercise I want you to do. Can you just continue the trace? Continue the trace with more occurrences of the old events. You can see at the moment, the variant value is still 0. So if you try to evaluate the guard of ILN and ILOut, they're both still disabled. So how can we actually make sure we can still take further occurrences of the new events? We definitely don't want them to diverge, but we also don't want them to be not available forever, right? So how can we actually make it happen? It turns out the only way to really increase the value for the variance is by MLOut, as we did earlier, right? With occurrences of MLOut, such that new occurrences of ILN and also ILOut becomes possible. That's the exercise I would like you to do. Right, let me highlight it. It's a very important exercise that I really want you to really continue with the trace that we have gone through so far. You can imagine that the diagram, if you keep tracing, is going to basically go above and above like before. And then from that point onwards, we can actually try to take new occurrences for ILN, ILOut, and it will decrease the variance as well. But the pattern is going to be clear. Always the value for the variance should really stay either 0 or above 0. All right. So the final exercise, let me try to highlight it, and then we are done. The exercise would be you actually want to continue with the trace with occurrences of the old events MLOut, such that new occurrences of ILN and also ILOut becomes possible. All right. So that'll be the exercise I assigned to you. Alrighty, so let's now move on to talk about how we can formulate such variance in our proof obligations.